With an R? Who, what, huh?
Reggae.
Rugae.
R-U-G-A-E.
Uh-huh. All right, so what we're looking at is this, a cartoon version of a gastric pit. So this thing right here, ladies and gentlemen, is going to be this thing right there, all right? And bless you, I'm looking at just one of those little parietal cells, maybe that guy right there, right? And there's the top, all right, where my simple columnar cells are. So this orange region is this part right here on the whiteboard, simple columnar epithelium. And we're going to look at how we actually go about making hydrochloric acid. What's your favorite equation, by the way?
H2O plus CO2.
Write it down. Here it is. You thought I was kidding, right? We use this a lot. So here's the idea of CO2, again, plus H2O, because cytoplasm is mainly water, right? And that's going to create carbonic acid. Now don't go past carbonic acid.
Okay.
To make your diagram easier, do the proton next, do the hydrogen ion next, and then do the bicarbonate. You've already shown now where the hydrogen comes from for hydrochloric acid. Now let's get rid of the bicarbonate first. That's why I wanted you to write it last, because it's on the edge of our cell. And there's going to be this nice little proton exchanger right here on the basal side, and we're simply just going to pump that bicarbonate right into the blood. Kind of like we saw with the renal system. And we're going to exchange it for a chloride ion. It's going to come right inside. And that's where the chloride comes from of hydrochloric acid. This little shifting system here is responsible for what's called the alkaline tide. That happens in your blood, because the more bicarbs you create, right, the more alkaline your blood becomes. And some hypothesize maybe this is why some folks get the drowsies after they eat, because it's actual change in your pH due to the activity of your parietal cells. Now, I've got the chlorides, and they're an easy thing to do. They're simply going to come right through here through a leaky channel, and they're going to simply just diffuse right the hell out of the cell and end up in my gastric pit. So, no transporters, no facilitated diffusion. It's simple diffusion. Well, it's facilitated through a leaky channel. It's not facilitated by a transport device. The next easy one then is the hydrogen. So let's bring our proton up to here. And then let's give ourselves a proton pump. Well, it's called a pump. And we're going to pump the hydrogens out into the gastric pit. And in exchange, we're going to bring in potassium ions. This is an ATP-driven pump. So we're going to use ATP to get this thing to work. So we'll just put ATP right in here. Now we're going to name it. Let's use a logical name. How about a hydrogen potassium? I'll put the name up here so it's out of the way a little bit. Put it up here. A hydrogen potassium ATPase pump. If it walks like a duck, let's call it a duck. Now, the significance that all A&P books try to talk about is the fact that the parietal cell is not releasing hydrochloric acid. It's releasing chloride ions and hydrogens that can then come together to form hydrochloric acid. But they're also going to work their way up the gastric pit, because I got to get to the surface of the stomach. So this is going to migrate up. Right, the chlorides are going to migrate up. Then they're going to come out to here. They're going to come out to here. And I'll find all kinds of things. I'll find free hydrogens floating around. I'll find free chloride ions floating around. Probably even have some of the compound of HCl before it dissociates into its little individual species. but we want to have lots of hydrogens to attack the food. So I can do that chemical digesting and break down whatever that is, and with John's 30-minute rule, kill any pathogens that might be on the food as well. We know what can control the activity of the parietal cell's production, right? I've got histamine, I've got ACH, and I've got gastrin. We can all talk to our cells and have them be told to make more and more hydrochloric acid. So we're going to reposition our H2 blocker, or H2 receptor, I should say, over here. And I'll get out of the way here in a second. So there's my histamine receptor. Oh, creak. Now, one of the things we can look at is, I've got this nice little covering of blue mucus that covers epithelium cells. I guess maybe I should draw a few of those over here for you so you realize that they are actually covered by mucus. So I'll give you a few more epithelial cells over here, covered by mucus. And Stefan, what's that bacteria again that lives in your gut?
Helicobacter pylori.
Whoa, gotta go a little slower for them.
Helicobacter pylori.
You guys remember about Helicobacter pylori or H. pylori? From, yeah, that one you recognize, right? They're going to live in the mucus because they eat protons. So we're going to draw some little H. pylori buggers. That'll be these guys. We're going to put them in here and in here. We're going to put some of them in here. We're also going to have some right here where there is no blue mucus. I don't think that's going to be sharp enough. And when you get an overabundance of H. pylori, it can create inflammation and irritation. So we're going to get inflammation. I'm using red because it's representing blood and bleeding. We're going to get irritation of this tissue. And that's going to then lead to an ulceration. Because I now have epithelium that's not covered by mucus. And these hydrogens can be coming down and literally attempting to digest the epithelium of your stomach lining. And you're going to call that a gastric ulcer, because you have an ulceration of the gastric epithelium, simply due to lots of H. pylori irritating the epithelium. They can't make mucus. Therefore, they're now susceptible to the contact of those little hydrogen ions. So when you have the idea of H. pylori, does anybody know what they do for the treatment of H. pylori? Stefan, do you know?
I'll tell you later.
Okay. So one of them is antibiotics. Right? When I had a roommate in college, my first time in college back in, well, a long time ago. And he was given an antibiotic. All right, well, antibiotics aren't necessarily that specific sometimes. You have a broad spread antibiotic that can affect other types of antibacterial, can affect other types of bacteria in your system. And we realize now we don't want to be that broad in our approach, but antibiotics is one way to attempt to reduce the number of H. pylori. But the risk is, how to put this, the healthy bacteria are affected. And we don't want to affect the healthy, good bacteria. Because we're beginning to realize that the bacteria that live in you are way more beneficial than we gave them credit for just 20 years, just 15 years ago. Now, the physician might say, well, all right, H. pylori might be the cause, it may not be the cause. I want to take a different approach to reducing your gastric ulceration. You go, okay, what's the problem? The problem is hydrogen ions are attacking my epithelial lining. So what if I give them a rest from all the hydrogen ions that seems to be bombarding them? Okay, I could do that. How would I go about doing that? Well, I know the cell that makes hydrogen ions, it's a parietal cell. I know how they make hydrochloric acid. So why don't I attack how the cell makes hydrochloric acid? So we're going to come down here, and I know about this little thing called the proton pump. And let's see, what color should we use? I guess I'm kind of stuck. We'll use red so it stands out. Why don't I take what's called a PPI?
Proton pump inhibitor.
Say it louder, David.
Proton pump inhibitor.
Because what is it doing? It's inhibiting the proton pump. Inhibitor. And we're going to show that with a PPI coming right down here and doing a negative feedback or inhibition symbol onto that proton pump. And the proton pump can't work, guess what can't come out into the gastric pit? Hydrogen ions. If you can't have hydrogen ions, you can't make hydrochloric acid. That sounds pretty good. Now I have a way of controlling the amount of acidity that my poor little cells are exposed to. There is one other way to do it, that maybe you don't want to take a proton pump inhibitor approach. And I realized, well, there's also this avenue. And I can come down and do what's called an H2 blocker. And I can actually block the H2 receptor. Then they got a better tube. So H2 blockers are going to come in and prevent histamine from binding to the H2 receptor. And you don't need to know the mechanism, but eventually you're going to make less hydrogen ions. Hydrogen ions. Going through puberty again. Now you guys actually recognize these. Maybe not by the formal name of H2 blockers and PPIs, but you ever seen these commercials for Xantex and Prilosec? Xantec is an H2 blocker. It has a similar shape, yeah. I thought you said the same shit for a second, going, wait a minute. Roughly the same shape as histamine, yes. And Prilosec is a PPI. It's a proton pump inhibitor. That's easy. Prilosec with a P, right? Proton pump inhibitor with a P. Nexium is also a proton pump inhibitor. Tagamet and maybe Pepsid AC, right? They're all H2 blockers. And now you know they're known as OTCs because you need prescriptions in my day to get these things. Now they're over the counter. And just to really drum in this idea, right? Whenever you guys take medication, whether it's a Tylenol, an aspirin, or a PPI, right? Or a diuretic for that matter, right? That medication is not going to make a beeline for the thing it's designed to attach to. It's a random statistical chance opportunity. So some of my medicine will bind on some proton pump inhibitors, and some proton pump inhibitors won't have any medication attached. They'll keep working. So if I don't get the desired effect, I simply just take a stronger dose, which means more of those molecules to play musical chairs and a better statistical chance of getting more medicine on more pumps. But just because you take a PPI doesn't mean all proton pumps stop. Only the ones that get bound by the medication. But that'll give you 3 avenues of approach, perhaps, for ulcerations. If you think it's due to H. pylori, I can maybe think about an antibiotic. But there are consequences to that. It might be affecting healthy bacteria that produce a lot of your serotonin, that we now realize mainly comes from your gut, not your brain. So depression that is of mild clinical significance, where they give you an SSRI due to a low level of serotonin, might be actually due to case history of, well, get off the damn antibiotics and maybe you'll be okay. So there's a whole new avenue we haven't even thought about that's coming into approach for us to think about. There's about, well, I've heard different numbers from 700 to 1,000 different types of bacteria living in your gut, and probably all playing a really important role for your overall health of the system. So since we're on that quick little top, now we'll say the topic for the diarrhea conversation. All right, hang on. So, you guys okay with this? Parietal cells use CO2 and H2O to make protons. I pump them out with a proton potassium pump. I can use a PPI to slow down the activity of that proton pump. My stomach is covered in blue mucus to help prevent red inflammation from attaching or attacking those cells. I can use PPIs, H2 blockers, or antibiotics to treat an inflammation of my stomach lining. Some common drugs are things like Nexium, Pepcid AC, Tagamet, Prilosec, and such. You guys okay with that? All right, take photographs before you leave really quickly. All right, and sign contracts. Photograph.
Thanks.
But not just this, of our other conversation as well. The rooms,
Oh,
the place.
The whole place.
Cover your ass.
I will.
Okay. All right, so this is from your book. They're basically doing the same kind of conversation, but there's also inaccuracies in it. You gotta be careful of sometimes what they're trying to say and how they're saying it. So they're showing me the CO2 idea, and we don't need to worry about how the fact that actually water can also contribute to hydrogens, but you know, we're doing the CO2 plus H2O conversation. They're showing me the hydrogen potassium pump, all right, but where the frick's the potassium, for God's sakes? Oh, God, okay. And then this thing. I'm getting the impression that bicarbonate simply diffuses through the cell wall into the blood, and the chloride simply diffuses from the blood into the cell, right? That's where you need that one big proton transporter right there. Has to be right here. They're not showing it to you, but it is one protein that is shifting the bicarbs out and bringing the chlorides in. And they didn't show any leaky channels over here. It's not simple diffusion. But the basic idea is there. CO2 makes bicarb, bicarb goes into the blood, the hydrogen from my CO2 conversation gets pumped into the gastric pit, it joins up with the chlorides to form hydrochloric acid. That's all happening right along in here. And then it works its way up, and then gets to the surface where you can digest your hamburger, cheeseburger, your tuna fish from the vending machine, whatever it happens to be. All right, let's start looking at gastric activity and how this is going to work. So the top line says increase in gastrin and the red word motility. Motility means the contractile behavior of your stomach, the contractions your stomach makes. I want you to think about your stomach as mainly a gigantic mixing bag full of hydrochloric acid and some enzymes. That's its main purpose. You actually don't do a whole lot of digestion, and you do very little absorbing. Mainly a storage bag to mix the food up. We know some of the things that will activate our gastric activity and our motility. It's going to be proteins, right? Landing on G cells, right? Caffeine, alcohol, even acetylcholine can all trigger gastrin production. This is the one that's going to be a little hard to think about in terms of increased pH as a stimulus for this. So let's think about this to maybe help you get the idea of how an increase in pH is a stimulus. Here is a big gigantic pot, and you start putting food inside of your pot. Lots and lots of food. Well, as soon as I start putting food in my pot, my stomach, I start making some hydrochloric acid. But I've got more food than I do hydrochloric acid. And it's going to start soaking up those hydrogen ions like a sponge, kind of removing them from the environment. They're not actually able to raise the pH, or sorry, lower the pH because there's so much food. And you keep adding food, you keep eating, until finally you stop eating. Now, no more food's going to come in. And eventually, over time, right, I start making more and more and more and more and more and more and more hydrochloric acid. The pH begins to lower and lower and lower because we're doing this, right? Due to the amount of stretch, due to the amount of signaling, and as my pH begins to get lower and lower and lower, which means I start making more and more hydrogen ions that can actually affect the pH, I start sending this signal to the D cells to help regulate the overall production of hydrochloric acid. But at first, right, think about how when you're really, really starving, and think about maybe some hydrochloric acid now being released in anticipation of the food you're eating. You start dumping Dick's French fries in there and a milkshake and a cheeseburger. Now I'm soaking up all that acid. That's going to raise my pH. That tells my body, hey, there's food in your stomach. Let's start releasing gastrin so we can release even more hydrochloric acid. And depending on how much you ate, right? Whether it was one cheeseburger, or how about 3 half-pound cheeseburgers, 2 orders of fries, and 4 beers, right? You get a lot of stretch with that. That's my body's way of saying, God, he's still eating for God's sake. Let's keep making more hydrochloric acid to handle all the food you consume. So it's kind of like a per volume basis. The more you eat, the more HCl we produce. The less you eat, the less HCl you produce. Because why make more than you need normally? Does the idea of the increased pH make sense? Yeah? No?
Yeah. Yeah.
Okay. Just think of it as let's just try this. This is another way of thinking about it. Picture a beaker of acidic solution. And you start adding a buffer to that acidic solution. What's going to happen to the pH of that solution if you add a buffer to it? Start going up, right? Well, food is a buffer. The amino acids, the proteins can soak up lots of hydrogen ions like it did for the renal system. Why hydrogens don't go into the filter right off the bat? That means I'm raising the pH. That tells your body, hey, start making more hydrochloric acid. Eventually, though, you stop adding more buffer to the solution. You start adding more acid to the solution, which is this hydrochloric acid from the parietal cells. And over time, the pH of the stomach will begin to decrease. And as the pH begins to decrease, we start shutting down the activity of the chief cells, start shutting down the activity of the parietal cells, and we start shutting down the production of G cells. It's not a shut-off, it's a volume control issue for all 3 of these. We start doing less of their behaviors. But now there's a problem with that. Because you've been eating so much, and now we have so much hydrochloric acid in our stomach, I've really lowered the pH. Does anybody remember the pH value I said that your lingual lipase and salivary amylase actually work good in? It's a 5 to a 6. We're going to lower this pH all the way down to a 1.5 to a 2. What's that going to do to the behavior of salivary amylase and lingual lipase? It's going to denature them. It's going to shut down their behavior. So that means now we're screwed with our carbohydrate digestion and our lipid digestion, unless other enzymes start showing up. So we're going to start getting another enzyme, the pepsin. And pepsin does like a really acidic environment. But those 2 earlier ones, of salivary amylase and lingual lipase, they don't like really acidic environments. So we've lost their ability to work with us. We're going to have to replace them with pancreatic enzymes later in our intestines. But right now, we're only doing the carbohydrate and fat digestion due to the acidity of our stomach itself with the chemical digestion we get from hydrochloric acid. Now, we're not going to call the food in your stomach food in your stomach. We call it chyme. And there's a certain texture we want to get to with the chyme in our stomach. So go back to the idea of what your stomach really is, a big gigantic storage bag. You're going to dump in there chunks of half-pound cheeseburgers, fries, beer, some chicken wings, and maybe just to be healthy, consciously, a bit of a salad. Alright? Just so you can feel better about yourself. Alright? That's what I did during my summer vacation. Now, put it in a big blender, hit pulse. Alright? I want to turn that into a rather liquidy, almost not a baby food puree, but like minestrone soup texture. Right? And here's how you know this. Just to put it in context of real world scenarios. The last time you guys threw up, what did it look like? That's kind. That's what we want, right? I can't have big chunks of food getting into my small intestine. I need to create a liquid slurry. And that's the whole purpose of this. And to create that really gross slurry effect, you have a really talented stomach. It will take the chunks of food, right, and will begin to chemically digest into a more liquidy-like environment. And the liquidy part is what gets to leave. And they're trying to tell you that with this little diagram here, but this is a much better image to think about. The blue arrows are the liquidy stuff, and the yellow gold arrows are the more chunky stuff. And those of you who already had lab, remember I talked about the fundus in the body and the different cells that are found up here? Up here where it says body, that's where you have your chief cells and your parietal cells. Those are the cells that can turn my chunky stuff into liquidy stuff. I want to send the chunks back to the place that they can be broken down into. If you're already liquid, I'm going to go into the pyloric region so I can squirt you out in what we call a bolus, a little chunk of food. I thought they used the word bolus here, they didn't.
It's up
They
top.
did up the top for incoming food.
Oh, for incoming food, yeah.
Yeah.
All right, so that little bolus there is the same idea here. That's a bolus. It's about 2 tablespoons. We want to do a Lucille Ball chocolate factory scenario all over again. I want to control how fast the food leaves the stomach. And a part of that is, if you're not liquidy, you're not leaving. Go back to the part of the stomach that can turn the more solid stuff, right? The more solid stuff into the more liquidy stuff. And those of you that already had lab, we talked about the body, where we have chief cells and parietal cells and the fundus. That's why I'm sending them back up there, so I can turn it into a more vomitous-like texture. Speaking of that, the last time you guys had to unfortunately throw up, or be with someone that throws up, put this in the back of your mind. What was the texture of the stuff I just threw up with? I remember one time in college, my dad came into Dallas, we went out and had raw oysters. Yeah, oh God, that was not a nice night.
In Dallas? Bad place.
No, it was a very high-class restaurant in Highland Park. This is a pretty wealthy part of Texas.
Still too far from the ocean.
And I got food poisoning, and every 20 minutes on the dot, I had to go to the bathroom. And thank God we had our own private bathrooms, because I went to a private university. We had our own maids, we had our own bathrooms. It got to the point where I simply just put the trash can next to my dorm bed, because both ends were going. And just like, there's no way I'm going to make it to the bathroom. But I remember the very first time that actually, yeah, oysters came out. Because they hadn't been in there that long. I could still tell when I was eating. But you ever had vomitus where it was really, really liquidy? Wasn't very chunky? You really couldn't tell what it was that was coming up? Well, when you guys throw up, it isn't just from the stomach. It's about halfway through the small intestines. And the body goes, okay, where's John's shortest point of exit? Well, we have a tie, both anus and mouth. So you get both ends going at the same time. But if it's more toward the stomach, then we're going to relax this sphincter. We're going to relax it. And the stuff in your small intestines is going to come right back up and leave your body, which is why it's more liquidy than the stuff that's more chunky. If you throw up and it's really, really chunky, you know it hasn't left the stomach yet. But if it's really liquidy, then you know it's actually left the stomach, gotten into the small intestine, and the shortest way out was not through the anus, but through your mouth. And that's why it has the material that it does. Oh, don't worry, we'll do a diarrhea conversation too. Okay? But you might as well know why you're getting what you're getting when you get these various types of vomitus with this.
Can't wait for the next time.
Oh yeah. Okay, now, we just finished the gastric regulatory process, right? I know that what increases stomach behavior is increase in pH, acetylcholine, gastrin, alcohol, caffeine can all play a role to stimulate the activity of my stomach. And it's really just a big gigantic frickin' mixing bag to mix the food with the acids and the pepsin, right? And what you want to think about it is this fashion. I want to make puree, but also the idea of, anybody here bake bread? Make flavored breads, like maybe rosemary and garlic and herbs. Do I just simply sprinkle the herbs on top?
No.
Right? You incorporate it into the dough, right? You knead and fold, knead and fold. I want to incorporate the acids into my food. That's why we have this contraction behavior of our stomach, to really mix and fold and expose all surfaces with lots of hydrochloric acid and lots of protein enzymes if I have protein in my content. But by the time we leave the stomach, we're going to enter the first part of our small intestine called the duodenum, for those that haven't had lab yet. And for those that haven't had lab yet, and to reiterate those of you that have, the function of the duodenum, remember, is to control the rate of gastric emptying. To control the rate of gastric emptying. How fast does stuff get to leave my stomach? And that's the job of the duodenum. Now, how does it do that? A couple of ways, actually a fair number of ways actually. Think about this little idea right here of the analogy of our stomach. This would be your esophagus, and those of you that have had lab, right, there's your lesser curvature, this is your greater curvature, right? An over-exaggerated pylorus, the nice little sphincter, and then this could be my duodenum. So the food that's in here, right, is going to lead through the sphincter and get into my duodenum. Well, your duodenum is a tube, but it's a closed, squished tube. There's no space in there, really. I mean, if you put your little finger in there, you're going to be hugging the walls of the duodenum. So when food gets in there, any amount of food is going to create a bit of stretch automatically. And that little bit of stretch will increase the diameter of your duodenum. And we have stretch receptors in the wall of your duodenum. And that's going to create basically the idea of distension. Where'd my little toy go? Okay, I'm losing my marbles. All right, guys, what do I do with it, for God's sakes? Looking for my laser pointer for crying out loud.
Right here.
Right there.
No, that's the case for it. Okay, that's really interesting, all right. So let me grab my "you shall not pass." All right, so we get distension, all right? That's A, because of the arrival of chyme. The mass of that stuff automatically creates volume that pushes it out. But part two of this is this little story. I can use these two colors. Let's do it this way. So here's your esophagus, here's your lesser curve, here's your greater curve. I'm now going to destroy the relationship structurally. This is going to be my duodenum. This big thing. So we have room to create symbols with. And then this is going to be a capillary bed running right along next to the cells of my duodenum. This will be blood. We're going to pretend that there's simple columnar cells here. I've got food, what we call chyme, right, in my stomach. Some of that will go into the duodenum. And by sheer volume of stuff, that creates a certain amount of stretch. But we're going to add to that stretch. because you've got a bloodstream right next door to it, and I have a relatively hypertonic environment. Compared to blood. What comes to mind when you start hearing the word hypertonic? And what is blood mainly comprised of?
Water.
So we got water and hypertonic. What are you thinking about? Osmosis, which is what? The diffusion of water from regions of higher concentration to regions of lower concentration through a cell membrane, for God's sakes. You got to add that. I've got endothelium of my capillaries. I've got the epithelium of my duodenum. And the water that is in your plasma will be osmotically attracted to the hypertonic value of the chyme in your duodenum. That creates even more distension, even more stretch. Not a lot, we're talking millimeters, but in terms of stretch receptors, it's like, hey, holy crap, that's a lot of movement going on here. Now, why do we care about the distension of the duodenum? Due to first the volume of food, but then the also added effect of water osmotically moving in, because that distension creates what is known as the enterogastric reflex. This is really bugging me. Now, there it is, you little SOB. You guys are taping me, and I get to watch it. All right, put a big star next to this, enterogastric reflex, because you're going to screw, no, you're not going to, let me say it this way. There's a chance to screw it up. You guys are all smart enough not to actually screw it up. Look at the name, all right, enterogastric, due to distension of the duodenum. Now, here's why I want you to put a big star next to it. That's in purple. Let's go a few slides forward. That word in red. Look familiar? It's just a frickin' opposite of the purple word. And you guys tend to get these mixed up. All right? How do I know that? Because I just got done grading my Bio 242 exams at Seattle Central, who just finished their digestion unit. And several students got these flip-flopped. All right? Because they're the complete opposite. Here's how you can get them straightened out. How I warned them. I always warn you guys. The first part of the name tells me where the signal came from. The second part of the name tells me the target of the signal. Entero refers to intestines. So it's an intestine to the stomach reflex. That means we're going to slow down stomach activity. So the first part of the name is where the stimulus comes from. Second part of the name is the target of that stimulus, of that signal. Now, what does the enterogastric reflex do? It decreases gastrin and motility. So in other words, we're decreasing all of this stuff. We're decreasing all the whiteboard stuff. We're basically saying, hey, you just gave me a big mass of food. Let me have time to handle it, for crying out loud, before I have more. And how can I really make sure that I control how much comes out, besides decreasing the contractions of our stomach? Look what I do to my pyloric sphincter. That sphincter right there. I increase it. I make it even tighter, so less stuff will leave. I also do what in terms of mucus production?
Increase.
Right? Do you guys see how we increase mucus production? Right? It says so right there. Why are we doing that? Look what just got in there. Right? Stuff from the stomach. How acidic is stuff from the stomach? It's a pH of 1 to 2 at most. That's really acidic. So I want to reinforce the protection by not only having my cephalic phase prepare me with Brunner's glands, when the chyme actually does get there, creating stretch that will also tell the exact same cells, get off your butt, Brunner's, and make me more mucus. Because now it's putting our money where our mouth is. The chyme is here. The pH is actually here now. Because that pH, remember, is going to be really, really low. It'll be a pH of approximately, well, approximate symbol. Usually 1 to 2, depending upon what you've eaten and how much time you've had and all that stuff. And I want to protect that.
So the extra water from the blood doesn't significantly raise the pH?
Not significantly, it does a little bit. That's gonna be part of the things that are gonna help us out as we kind of move along the length of our tube. We'll get more water to do that, which help raise our pH as we go about doing this. Now, that's the official end for tonight, but hang on here. All right, so we are going to walk through these following slides: the VIP, the GIP, the CCK, the secretin, and gastrin. Those are all different hormones coming from cells that are lining your small intestine, called enteroendocrine cells. They're not just in the stomach, but those enteroendocrine cells are going to be lining my duodenum. And these cells are going to be monitoring what's in the chyme and releasing the hormones that are necessary based upon what we find in that chyme. So if you want to begin memorizing all these different hormones, the VIP, the GIP, the CCK, what they do, you can get a head start for Wednesday. We're going to walk through each and every one of them one at a time.
You're going to go over them again on Wednesday?
Oh yeah. It's just if you want to get a head start, like some people may want to do who write too much on exam questions.